Hi, welcome to the third of three videos that deal with solving simultaneous equations in 2 or 3 variables. In the first video, we looked at the condition in which the solution exists for 2 and 3 variables, and in the second video, we looked specifically to solving 2 simultaneous equations involving 2 variables using matrix methods. And if we just quickly recap that, here are our 2 simultaneous equations in the general form. We can write that in matrix form, as shown, and solving that matrix equation, we get the solution for variables x and y. If you've seen the second video, you might recall that the denominator a1b2 minus b1a2 is the determinant of the matrix. There we are. And that the solution only exists if the determinant is not 0. Now let's move to solving simultaneous equations involving 3 variables, x, y, z. 3 methods will be shown. The first method is called the adjoint method, or using the properties of what we call the adjoint of a matrix. And here are 3 equations with 3 variables, x, y, z. We can write that in general matrix form. So we have matrix A, which is a 3 by 3 matrix. That means 3 rows, 3 columns. And then we have our variables x, y, z in the next matrix over here. And another matrix which represents the right-hand side of each equation. Now the aim is to manipulate the left-hand side of the matrix equation so that we end up getting the identity matrix represented by the letter I, and to do that we work out the inverse of matrix A represented by a to the minus 1, and there's the identity matrix represented by I. And when we work out the inverse matrix, the property, of course, of a matrix with its inverse is that the product gives you the identity matrix. So when we find the inverse matrix, pre-multiplying both sides of our matrix equation by its inverse will give us what's shown here on the right. And of course, multiplying by the identity matrix is really the same as saying multiplying by 1, so that doesn't change the result. So in effect, we have our solution for variables x, y, and z by saying that x will equal the inverse matrix A multiplied by D1, and y will be inverse matrix A times D2, and so on, like that. Now the question becomes, how do we find the inverse of that 3 by 3 matrix? There's our 3 by 3 matrix A, and we want to determine its inverse. There is a method we follow, which is shown there, that the inverse matrix A is what we call the adjoint of matrix A divided by its determinant. Now we know how to work out the determinant of a matrix, of a 3 by 3 matrix. That was shown in video 1. What we need to do in this video is to work out how we go about working out adjoint A. And there are several steps to do that. Firstly though, let's work out the determinant of A, which we already know how to do. There's our matrix A. In video 1, the method was to use any one of these 6 equations, that means any one of the 3 rows or any one of the 3 columns, and work out the value of the expression. Doesn't matter which one you use, they will all give you the same value for the determinant. Step 2, to work out the adjoint of matrix A, firstly we interchange the rows with the columns. What we get at that stage we call AT, which means the transpose of matrix A. Transpose means replacing or interchanging rows with columns. So there's our matrix A. Let's see if we can work out what the result will be when we interchange rows with columns. So the first thing is we swap row 1 with column 1, and it looks like that. Then we swap row 2 with column 2, and finally swap row 3 with column 3. So on the right we have our transposed matrix. Now there is a fast way of transposing rows with columns. If you want to do it this way, you might notice that the leading diagonal from top left to bottom right remains unchanged, so you leave that alone. And then really what happens is each pair, like that, is swapped. Okay, that's step 2. Step 3, once we have the transpose matrix, we then find all of the cofactors, and this is what it means. Looks a bit complicated, doesn't it? But it's not that difficult to understand. Also, it was pointed out when we were working out the determinant in the first video that each position in the matrix alternated with a plus and a minus shown in red. That still remains the case here when we're working out the cofactors. And then in each position we put in the determinant of the 2 by 2 matrix, just as we did when we were working out the determinant of the whole matrix. So for example, in the first position for A1, the determinant that goes with it is that one there, and we obtain that by using everything that remains when we delete the row and column containing A1. And then we do the same thing for each of the other cofactors. So we have our 9 cofactors. Okay, let's apply all that to the example shown here. We have our 3 equations, 3 variables x, y, z. First step, there's the coefficient matrix A, which consists of the coefficients of each variable in each equation. Let's work out the determinant first of all. I'll choose row 1, but remember you have 6 choices. And if we work out the determinant using row 1, that's the start expression. And finally, getting a value of -1 for the determinant. Okay, that's one of the values we need. Next step, work out the transpose of matrix A. Now remember, that means interchange rows with columns, and that's what you get. And then using the transpose matrix, work out the cofactors. And that's the start of it, by replacing each position of the transpose matrix with its cofactor. And then when we work out each expression, that's what we get. For example, for the first one, where we have -3 plus 2, it comes from saying the determinant of this expression, which means -1 times 3 minus -2 times 1. And then working all this out, we get our adjoint matrix. And now applying the expression that we have for working out the inverse of matrix A, it's the adjoint A divided by the determinant of A. The determinant of A, of course, we worked out to be -1. There it is. So it's 1 divided by -1. And there's our adjoint matrix on the right. And then just simplifying that, 1 divided by -1 is -1. So we can divide each of these values by -1, and we obtain these 9 values there. And now we write our 3 equations in matrix form. There they are. Pre-multiply each side of the equation by its inverse that we've just found. Of course, why we did that is because there's the inverse, and when we multiply it by the matrix, they should give us the identity matrix, like that. Here's our identity matrix here. And of course, when we multiply x, y, z by the identity matrix, we obtain x, y, z. Carrying out the multiplication on the right-hand side, first step, we obtain what's shown here. And then just simplifying each row, we obtain 1, 2, 3. So what does that mean? It means that our solution for the 3 variables is x equals 1, y equals 2, and z equals 3. And geometrically, that means that each equation represents a plane in 3 dimensions, and our solution, x equals 1, y equals 2, z equals 3, is the intersection of the 3 planes. That was method 1, the adjoint method. Another method that's commonly used is called the Gauss-Jordan elimination method. And basically what that means is that we manipulate each row of the matrix, the coefficient matrix A, so that we end up with the identity matrix rather than finding the inverse matrix directly. There's our general form of the matrix equation, and that's what we want to end up with, so that we can state then that x equals d1, y equals d2, and z equals d3. Let's apply that method to the example we did in the previous section, where we know that the solution was x equals 1, y equals 2, and z equals 3. Now remember, we are trying to obtain the identity matrix. That means that that matrix will end up having 1 for the leading diagonal and 0 in every other position. Now there are different ways of doing this. There's a bit of trial and error involved. Depending on how you can see what operation is the most efficient, it will require a different number of steps. Now, just to make things a bit more efficient in the working, we can write that equation, that matrix equation, as we can see on the right hand side. The numbers in red are just simply to refer to row 1, 2 and 3, and we've left out the matrix x, y, z because that will remain unchanged each time. Alright, here's one thing we can try, and I'll just explain the terminology here. What this is saying is that row 1 will be replaced by, that's what the arrow means, by what's already in row 1 added to row 2. In other words, when you add row 1 to row 2, what you get will be the new row 1. So if we look at the diagram here on the top, row 1 plus row 2 will mean 1 plus 2, 1 plus negative 1, 1 plus 1, and 6 plus 3. That's what it will look like. Notice that we have a 0 there. That was the whole point. We want zeros there, 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 and there. And of course we want the leading diagonal to have 1. But that's a start, isn't it? Let's try something else now. What about if we replace row 3 with 3 minus 2 times row 2? That means we double each element of row 2, and whatever we get, we subtract it from what's already in row 3, and the result will become our new row 3. And when we do that, that's what we obtain. So we now have an additional 0. That helps, doesn't it? Something else we can try now. Replace row 2 with doubling row 2 and subtracting from it row 1, and we get what's shown there. So we have 3 zeros so far. We're getting close. Now we can multiply row 3 by 3 and subtract from it the elements of row 1, and that will become our new row 3, like that. And then replace row 1 by row 1 minus twice what's in row 3, like that. Notice there's only one more element here that we need to change to a 0. Can you see how that might be done? This is one way of doing it. Multiplying row 2 by 3 and subtracting from row 1. And that will become our new row 2, like that. And we're just about there. The only problem is that in the leading diagonal, each of these has to be a 1. So what we can do is, to change that 3 to a 1, we can divide every element by 3. And to change that 6 to a 1, divide each element by 6, like that. First divide by 3, row 1, and then divide by 6, row 2. And we have the final form of what we require. So that is now our identity matrix. And now we can read off our solution straight away. We can say then that x has to equal 1, y has to equal 2, and z equals 3, as in the previous method. Just to reiterate, this is a almost stab in the dark method. There's a bit of trial and error. There's a bit of thinking about what's the best approach to take, and certainly there is no set number of steps you need to do to get the solution. This required 8 steps. You might find a way of doing it in less than 8, or you might find a way that requires 10 steps or more. It doesn't mean it's right or wrong. It's just a matter of the efficiency or how much time you're prepared to spend using this method. Okay, finally the third method, Cramer's rule. This is probably the most direct method, probably the easiest and the fastest. Again, let's look at our three equations in matrix form. We can write down the solutions readily using the coefficients we have. To work out the value of x, it's the determinant of that 3 by 3 matrix divided by the determinant of matrix A. Now, that 3 by 3 matrix is our original matrix A, but you can see what's happened. Column 1, which contains the coefficients of x in each equation, have been replaced by this matrix, D1, D2, D3. Can you predict what the corresponding expression for the solution for y is going to be? There it is. Very similar, except that the second column containing the coefficients of y have been replaced by D1, D2 and D3, and not surprisingly the expression for z is the same, but the column for z has been replaced by D1, D2 and D3. So all we need to do is work out each expression for x, y and z, and we have our solution. So let's apply that. The coefficient matrix A is as shown there. So we can work out the determinant of A, but we've already done that in the first method, which came out to be -1. Now to work out the value of x, just replacing the coefficients with the numbers we have. Here they are. And it's just a matter of working out the determinant of that 3 by 3 matrix and dividing it by -1. And there's the start of working out the determinant. And when you work all that out and simplify, you get a value of x equals 1. Similarly, to work out the value of y, subbing in the values, working out the determinant in the numerator, comes out to be 2. Similarly, for working out the value of z, subbing in the information we have, and then working out the determinant at the top, and then simplifying, we get a value of z equals 3. So this is consistent with our previous two methods of getting x equals 1, y equals 2 and z equals 3. I hope this has given you some insight into how matrix operations can be used to solve a system of 2 or 3 equations involving 2 or 3 variables. If you have any comments, please leave them, and if you have any other suggestions about other areas we can investigate that are of interest, also please let me know in the comments section. So until next time, bye bye.